So this experiment relies on PCR, or the polymerase chain reaction. And I invite you to look at all the videos that we are going to post on the polymerase chain reaction. These have been compiled by other groups. They do a much better job at illustrating how the process works than what I would do on a board. So it's a video animation that explains how PCR works, plus the reading in the chapter does a pretty good job as well. But using PCR, we're able to amplify DNA so this is, when I think about it, this is very similar to DNA replication, but it's targeted. So we're going to amplify things in vitro. So in a test tube, we are able to amplify regions of DNA that we are interested in. For experiment 1, we are going to target the actin gene and both forms of the actin gene. So you have the genomic DNA and the cDNA, just to remind you, that will be amplified through PCR. And in a PCR experiment, reaction that you set up happens again in a test tube. I'll remind you to look at Bernice's video on the PCR setup, how you would set it up in the lab. I'm going to go over the table that she used to make that reaction happen, or those reactions happen. But for a PCR experiment to take place, you need to add several components. In vitro, or to this test tube, starting with water. DDH2O is double distilled water, or as long as you use a molecular grade water that is free of any DNA and then any other potential contaminants. You need to use very sterile water for this, for a PCR reaction to take place, PCR experiment to take place. Then we use a reagent called 2X-MITAC. This is important because if you notice, there's a 2 in front of that X. That tells you this is a stock solution. This has the polymerase that is used for the amplification of the DNA. It has nucleotides, or the building blocks of the DNA, and other buffers along with the dye that makes it red. And that's important for gel loading later. We also use primers. So key to a PCR experiment are the primers that we're using, because that gives you the selectivity, or the ability to target the DNA that you're interested in. And you have a forward and a reverse primer. So DNA is double-stranded. We have to target both strands that complement one another and have the primers converge one another. So the direction that the DNA is amplified are facing one another, so that we are able to only target the region that we're interested in. In the case of experiment 1, I'll repeat again, we're amplifying the actin gene in both the genomic DNA form and also the cDNA form. And then, at least for now, I'm going to make a small alteration to this table where I'm going to have a kind of a subtotal of what is in the reaction before adding the variable of the reaction, which is the DNA. So the test variable, what we're interested in to see if there's a difference, is the DNA. So this will be both or either genomic or cDNA, and then we have a total. And learning how to set up a PCR table is just as important as setting up the actual reaction. Oftentimes, you have to tailor your experiments and make larger volumes or use less of a particular reagent or overall volume, so whatever suits the need. So if we look at it per reaction, this is one reaction, and this will be in microliters using the Greek letter mu, microliters. Let's say we're setting up a 15 microliter reaction. We will often give you or tell you how much to use of the additional components that are needed for this reaction. So let's say we need half a microliter of each primer. And we're also going to instruct you to use 5 microliters of DNA at a given concentration. So this is already, we've already factored in the desired amount of DNA that we want loaded in there based on its concentration. So in experiment 1, we're going to use 5 microliters of DNA to make a 15 microliter reaction. And if you look in the reading, you'll find the table already has this information loaded in it. I'm going to show you how to calculate these values, which is what you would do if you were given a different number. So let's pretend this is all you know about this. How would you fill out the rest? Well, this is the beauty of tables. This is a 2x concentration, so it's twice as concentrated as we actually want. We want to bring it down to a working dilution of 1x. So if you use the formula C1V1 equals C2V2, what we're really solving for is V1. So this cell right here, what would go in this space, is V1. So if you take advantage of the table, this is your V2 times, so 50 microliters times 1x. So rearranging for the equation, V1 equals C2 V2 over C1. This is 1x. This is 15 microliters. And you divide them by 2x. So 15 times the 1x, so 15 divided by 2 gives you 7.5 microliters. That's how we arrive at that number. So now you have one of these figured out. This will then just be the difference. So you have, add all the components and subtract those components from 15, and you find that you have 1.5 microliters for the water. Another thing you can check to verify is that the subtotal without the DNA, and I'll come back to why this is important, these numbers up here should add up to 10 because you're using 5 microliters of DNA. So this 10 is not part of this whole thing that we add up. This is a summary of what's up here, the components that we use for all of the reactions. Each individual reaction gets its own DNA. So we need to figure out the number of reactions that are necessary. So this is going to be a number, and because we want to make up this column here is what's going to give us the master mix, what goes into the large tube with all of the components, all these common components go into the master mix, but it's scaled up. So we need to scale it up, but we need to figure out how many reactions you need. So that number of reactions is going to equal n plus 2, where n is the number of DNA samples and 2 because it accounts for what we call negative control and a slush, or leftover this remains at the bottom of the tube that is not aliquoted into the PCR tubes. So, and you saw that in Bernice's video. So in experiment 1, we have n equals 2 because you have genomic DNA and you have cDNA. So those are your 2 DNA templates that you're testing, plus 2, so this number becomes 4. So you have 4 reactions. For your master mix. So now we just scale everything up except for your variable. You still need you're only testing 1 DNA sample, you're only testing one genomic sample, 1 cDNA sample, and a negative control. So the rest of the table then becomes 6 microliters, 30 microliters, so this is 40 microliters, and you'll remember from Bernice's video that she started with 30 microliters of the 2x tack in a microfuge tube, so a larger tube. Then she went on to aliquot it so you're evenly dispensing equal amounts of your master mix, and these are 10 microliter aliquots. So again, that's where that number comes into play. that is just a common reagent, which all of the reactions have in common. And she labeled each of the tubes genomic, it's a genomic G, C, and W. And now you add your each variable. So 5 microliters of the genomic DNA to the first tube, 5 microliters of the cDNA to the second tube, and then 5 microliters of water to the last tube for the water, the negative control. And negative controls are important because it's a reaction that should not work. It should not give us any result. We don't expect anything to happen if you put the negative result. That is a good baseline to compare the rest of the reactions to. If you don't have a negative control, it's hard to assume that your predictions are correct. So you want to incorporate this negative control. Other experiments, depending on if you have additional information, you can also include a positive control. Positive controls are tricky, so we're not including one of those in this experiment. And we'll revisit this concept of the controls that you use. So just to recap, for a PCR table, as long as you know your total volume, your concentration of TAC, and what else is given, you can calculate the rest. So if you're told how much of the primers to use and how much DNA to use, you can always solve for the amount that you need for the TAC. Again, take advantage of tables. You may not think about it this way, but this is already an embedded formula. You take the 15 microliters, divide by the concentration of your stock solution of the TAC mixture, and then that gives you this value. If you know either the DNA or the water, then you can solve the one that's not given. To figure out the number of reactions, again, we use a n+2 formula, and it might seem a little bit wasteful, but believe it or not, we often lose a lot of, even if you're really good with your pipetting technique, a lot of these solutions are a little bit viscous, and a little bit of the reaction remains in the tips as they're used. So we lose little of the reaction as we go. So there's why we account for a slush. So you have a little bit left over remaining in the original tube. And that's okay. The more reactions you have, the less slush you typically end up getting. In any lab we take, most labs should have their pipettes checked on a regular basis to reduce any errors. We want to make sure things are consistent from reaction to reaction, which is why in the negative control, I'm often asked, well, why can't I just leave the master mix, the 10 microliters without anything else? Well, the volume's different. Then the volume can have an effect. Typically it doesn't, but you never know, so you want to be consistent. So we'll be covering a lot more of the basics, and the polymerase chain reaction is one technique that we're using specifically for experiment 1, but it's pretty much the answer to a lot of the questions that are posed in this course. So a lot of the experiments are based on PCR techniques. So as a technique, PCR is important, and it's used in many different ways. So when you're thinking about why we're doing each experiment, think about for experiment 1, for example, the purpose of the experiment should be biologically based, not just specific to the techniques. So what is the point of the experiment? Well, we want to determine the gene structure of the actin gene in 4 different plants using the polymerase chain reaction to make more copies of this, which then we can analyze using gel electrophoresis. I invite you to make some predictions as to what you're going to see as a result of the experiment. And then we can also take this information, or take the products of the reaction and have them sequenced, and add that another component to look at the gene structure.